So an arrow with mass m is traveling horizontally at a velocity v when it hits a block of mass capital M hanging from a rope with length L. Consider the following two scenarios. The arrow is stuck in the block. How high does the block travel? So this first one is ballistic. This is a ballistic pendulum. And so the idea is you have an object and it collides and it sticks here. And this is a collision here. All right, so when you have a collision, you have a sticking collision, you want to do conservation of momentum. Now, what object should you be considering conservation of momentum is you should be considering the arrow in the block. All right, so what is the momentum of the block during this time, or the momentum of the arrow in the block system? Well, the arrow has a mass m with a velocity v, and the big block has a mass capital M and a velocity 0. So it's just mv here. Okay. Now, why is the momentum conserved? Is, well, clearly the block and the arrows exert a force on each other, but if you look at the only forces acting on it, on this system, are gravity, okay, and the tension force upward. All right, so these are the forces acting on it. So, but even though these are external forces, remember my system's only the arrow and the big block, right? So the rope is external and the earth is external, and those are external forces. However, they do not exert any force horizontally. So horizontally, the momentum is conserved because there are no horizontal forces acting on the system. So if there's no horizontal forces, there can be no change in momentum, thus conservation of momentum in the horizontal direction. Okay, so now the two objects are moving together with some velocity v here. We'll call it v2, just, I don't know, something different from this v here. So now these two objects are moving together, and what is their momentum? Well, the two objects have the same speed, so you can just lump the two masses together times v2. So this is the momentum after the collision. So we know during the collision, momentum is conserved. And so by conservation, we know that this is equal to mv. And so we can solve for v2, and that's mv divided by this quantity, little m plus big M. Okay. Now, that's first step of the problem. That allows us to get us that velocity. And then this whole thing swings upwards, okay, to another position here. And we want to know how high does the block go, okay? Now it's an energy problem because during the swinging motion, there's no work being done on the block arrow system. Okay, there's gravity and there's tension, but if you include, now we're doing a separate system. We're doing the arrow, the block, and the earth in that system. So gravity, while it's acting downward, it doesn't do work on the system because that's an internal force. And even though the tension is an external force, that tension is perpendicular to the motion, so it doesn't do any work on the whole system there. So we can say the kinetic energy down here equals the gravitational potential energy up here. And so there we can say, so that down here we have kinetic energy, which is 1/2 m plus big M v2 squared. And all of that gets converted into kinetic energy. And I want to know how high the block travels, so I want to solve for the h. Now the masses actually don't matter in that instance, but the v2 we solved here, we know that we can put that into there, so that's 1/2 mv over little m plus big M squared equals gh. And I just have to put the g divide by g to get on the other side. So I'm going to make it 1/2g mv plus little m plus big M squared equals h. Okay. Cool. The arrow bounces. Now this is a different scenario. Now instead of the arrow sticking to it, the arrow bounces off the block and travels backwards with velocity v/3. How high does the block travel? So now we have a different scenario. This guy we'll call v2 also, but it's just the block. The arrow is deflecting. It's bouncing off of that thing. Now, again, if you consider the momentum piece, right, the initial momentum, the momentum before the collision is just little m times v. What is the momentum afterwards of our little system here? Well, we have little m, but it's traveling in the opposite direction. Okay, so that's probably the negative direction, so we may gotta make that negative 1/3 v. And then the big block is traveling at velocity v2. Okay, and we can set these two equal to each other. So I have negative 1/3 mv plus capital MV2 is equal to little mv. I'm going to add this to the other side, so I get capital MV2 is equal to 1/3 plus 1 mv is 4/3 mv. And so V2 is 4/3 mv over capital M. Okay? And similarly, we do energy conservation. All right? And this time it's not the arrow, just the block and the earth, because we're talking about this conversion of kinetic energy to gravitational potential energy. So we're going to say down here we have kinetic energy, and it gets converted into gravitational potential energy. So that is 1/2 m, not m plus little m, but just m, v2 squared is equal to capital M gh. Okay, so that's 1/2 capital M. Oh, the capital M's cancel, so I don't need that. 1/2 v2 squared, that's 4/3 little mv over big M squared equals gh. Oops. And then just divide both sides by g, so I get 1/2g times 4/3 little mv over capital M squared equals h. So how does it? So did it go higher? The question you have to ask yourself is, the ratio m to, like, if you compare these two quantities, all right, this just has m over m plus big M. This has m over big M. So that's a bigger quantity because the denominator is smaller. It also has the 4/3 part. So overall, this quantity is going to be bigger compared to the other one.